Prime numbers look in a hopeless muddle, totally irregular sequence. Why is this? This is what we're addressing in this little video. The key idea that lies behind this video is very simple and can be illustrated from the recurring decimals. The first decimal that I want to consider, recurring decimal, is 1/7. Its period is 6 decimal places, and it goes 142857, 142857, 142857 to infinity, and we're looking at a section length of 30 decimal places. And because the section length of 30 is greater than the pattern length of 6, we see the repetition. The second example we're taking there is 1/97, which recurs in 96 places. Now we've only taken 30 decimal places there, and because that 30, which is the section length, is less than 96, which is the pattern length, we see no repetition at all, and it looks a total muddle. And that is why the primes look in a muddle, because the section lengths in general are less than the pattern lengths, and so no order can be seen. Now, the prime number sequence is composed of sections separated by the squares of the primes. We see the sections A, B, C, and we see the squares of the primes, 1 squared, 2 squared, 3 squared, 5 squared, and so on. Now, each section is taken from a regular sequence, whose different sequence is similar to a recurring decimal. So we could take a recurring decimal like 1/7, and that is what the different sequence is like in the primes. Let's have a look at what these sequences are. The sequence SM prime to BM, which is the group of primes 1, 2, 3 up to PM, first M primes, is perfectly regular, and its sequence, its different sequence, DSM, is like a recurring decimal. And we note that prime to 1 means divisible by 1. Prime to 2, of course, means not divisible by 2. We look at these regular sequences SM, prime to BM. S1 is the sequence of integers divisible by 1, that's to say 1, 2, 3, 4, 5, 6, 7, the integers themselves. S2 is the sequence prime to 2. We drop divisibility by 1, that's trivial now, and that gives you the odd numbers 1, 3, 5, 7, 9, 11. S3 is the sequence prime to 2 and 3. 1, 5, 7, 11, 13, 17, 19, 23, 25, and so on. The different sequences of these sequences SM are given here. DS1, the different sequence for the integers, is of course 1, 1, 1, 1. The different sequence for the odd numbers is 2, 2, 2, 2, 2. The different sequence for the integers prime to 2 and 3, that's DS3, is 4, 2, 4, 2, 4, 2. You can see the pattern length is getting longer. The sequence prime to 2, 3 and 5, that is S4, has a different sequence 6424242, and so on. And you can see that the pattern length has increased a lot there, to in fact to 30. Here is the third section of the prime number sequence, lying between 3 squared and 5 squared. 5 primes, 11, 13, 17, 19 and 23. Their differences are 2, 4, 2, 4, and that clearly has come from S3, which has a different sequence of 4, 2, 4, 2 forever. And we count that as a regular sequence because the differences repeat. So that's the third section of the prime number sequence. But when we come to look at the next one, we see it's irregular. Here now is the fourth section of the prime number sequence. We know that it repeats in 30 places, and we have a section of primes from 5 squared to 7 squared, giving you the primes from 29 to 47. That's a length of 18, but the pattern length is 30, and so we get no repetition when we look at the differences, which are 2, 6, 4, 2, 4. It's irregular now, and will be for every section of the prime number sequence after this. And this is why the primes are irregular, because the section length is less than the pattern length. In summary then, why do the primes look irregular? Why do they look such a muddle? Because the section lengths are less than the pattern lengths. Thank you. Hope I've persuaded you.